Thanks everyone for joining. I'm delighted to invite our guest speaker here, Boaz Barak, and he is a professor at Harvard, has done lots of really interesting things across several different areas of AI and computer science research, and now is also at OpenAI, and I believe is doing really interesting things on safety there that we will hear about. And this is related to a couple of papers that we sent around before the talk. And so we have a form that we sent around for questions, and we'll sort of moderate questions. But as questions come up, you can submit the form, and then we will, if we have time, ask Boaz at the end for any insights that he can help offer in addition to the talk. With that, I'll turn it over and take it away.
Thank you. And please stop me. You can feel free to stop me and ask questions. I'm not monitoring the chat, so you might maybe someone should stop me and talk if someone asks questions in the chat. I think your slot is pretty long, and I definitely don't have a lot of material, so there is no problem in taking more time. And also, at least when I used to teach at Princeton computer science, when I ran my hard papers in computer science seminar, I used to say, it was on Friday afternoons, and I used to say, I am not going to respect necessarily the ending time for this seminar slot, but I promise the students that I will always respect the date. And indeed, we never stayed in the seminar after midnight. So we can stay for longer if it's needed. And with that, let me talk about AI safety and inference-time compute. And again, please do stop me with any questions. So my plan is to talk a little bit about AI safety in general. And if you're interested in more of my thoughts on that, I fairly recently put out a blog with 6 thoughts on AI safety, which you can find here, and then discusses some of these things more in depth. And then I'll talk about 2 papers that demonstrates the promise of inference-time compute for AI safety. One is the deliberative alignment paper, and the other is on trading inference-time compute for adversarial robustness. And we'll talk about those in that order. So now that we have the plan, let's start executing on it. So safety, general notion is being safe from any harm. And at least the way I view AI safety is of being composed of 3 separate components, or which have some overlap between them. So one is alignment, and which is to ensure that the system follows the intent of humans. And humans can be different actors here. There could be the user of the system, there could be the developer of the system, there could be the regulator in the country jurisdiction in which the system is operated, and there could be other people involved. And part of being aligned is also understanding how to navigate when these instructions conflict and how to resolve those. Security is how do you maintain this alignment and following your instructions, even when some of the actors in the system and some of the providers of the input that you're seeing are adversarial and are trying deliberately to cause you to violate. And that could also include the cases that there are some of these actors are AIs that are adversarial, including maybe even the AI itself that we are trying to align. And the third aspect is generally what I call ethics, or maybe there is a better name for it, but even if the system is aligned and is secure, and it is precisely working as intended, it could still cause significant, potentially unforeseen and undesirable consequences just by using it as intended. So we want to understand what are going to be the direct and indirect impacts of deploying such systems on individuals and on society at large, and how do we make sure that these impacts are positive, or the positive outweighs the negative. And my talk today is going to be focused mostly on the alignment and security aspects of AI safety. So generally, I think probably everyone in the room is aware that AI is getting better all the time. So any kind of benchmark that we use to measure the performance of AIs as a function of time, it always goes up and to the right. And human performance is no barrier for the AIs to continue getting better, and there is no evidence of any slowing down. So with that, there is a question is, are we going to be okay? Should we be scared of these developments? And I don't know if I have like a perfect answer for that, but I'll tell you why on one hand I'm optimistic, and why on the other hand I also think we have reasons to be careful and to and not to assume that things will just go well by default without us having to do anything. So the main reason that I'm optimistic is that basically any kind of plot of human well-being is largely correlated with scientific and technological progress. So any way that you could measure human well-being, GDP, life expectancy, any other kind of metrics, you'll typically see that globally over the long scale of time and across a large population, these have progressed as we have improved in science and technology, and basically all kind of graphs of development look more or less like this. So in the long run and over the entire population, I think AI, as other technological revolutions, will have a positive positive implications, or at least that should be our default assumption. But the reason why I'm worried is looking at graphs like this, which actually looks like a good graph. Like right, we are this measures the airline fatalities per kilometers traveled, and generally we see huge improvements over the last 50 years. And even though, as we well know, this is still not perfect, we have seen that we can improve a lot in safety. But the reason why this is concerning is that it took us 50 years to improve. And in these 50 years, the basic functioning of the object that we were trying to iterate on its safety has not changed that much. Yes, it does. There have been some improvements in 2024 or 2025. Boeing 737 is not exactly the same as a 1970 Boeing 747, but it's not as different. And on the other hand, as people are very well aware, the amount of progress and change that we are seeing in AI is just like so much faster, and the difference between GPT-2 and O1 is probably more similar to the difference between a bicycle and a Boeing 737 than the difference between a 1970s Boeing and a 2020s Boeing. So we have less time and a lot of work to do, and we should take AI safety very seriously, and we should invest in it. And with that, I want to come to the technical part of the talk and talk about inference-time compute. Unless people want to ask me any kind of general questions now, or want to leave it also for the end, either works for me.
Why don't we leave questions for the end, and you can go ahead through these parts, and we'll probably circle back to the big picture part of the end of the question. We have a couple questions about big picture topics.
Sounds very good. Okay, so let me talk about inference-time compute. So generally, inference-time compute is the ability to spend an adaptive amount of computation for a given prompt by using variable amounts of, so we can do it in different ways. A typical version that's now popular these days is by using a variable amounts of chain of thought or reasoning traces tokens prior to the answer. But generally, we can think of inference-time compute as, the difference can be, you can think of it as the difference between Boolean circuits and Turing machines. So is COS 487 still taught at Princeton?
47?
I don't know.
Yes, theory of computation. So Sanjeev used to teach that. And so anyway, we can, the difference between, say, Boolean circuits and Turing machines is that Turing machines, as is well known, they can spend an arbitrary amount of time for a given input. That's why the halting problem for Turing machines is unsolvable. And basically, inference-time compute is the ability to endow neural networks with the same property, that they could potentially spend an unbounded amount of time for a given prompt, and it's not fixed in advance. And that kind of makes a lot of sense for several reasons. So one is that we clearly know that some problems are harder than others. So if you're always spending the exact same amount of flops, no matter what is your input, then you'll probably be underspending on some prompts and overspending on others. And the other thing is that even when we're fixing a problem, as we know, neural networks are probabilistic, and we could, they would have like some probability of maybe making a mistake or say some chance of solving a problem, and we could improve that chance by spending more and more inference time compute, and so increase the probability of getting the problem correctly. And generally, we have seen that this kind of works. So this is the plots from the O1 blog. And generally, we've seen that as we spend more inference time compute or test time compute, we improve performance on benchmarks. And that has been pretty stable finding across many different benchmarks. And so inference time compute is definitely great for performance of models. And the question is, can it help beyond these kind of maybe benchmarks that we mostly focus on that are easy to measure, like math and coding? And particularly the thing I care about is safety. And the main thing I want to talk about today is there's some evidence that this is the case and it can help with safety. So we'll first talk about deliberative alignment, which is about using inference time compute for reasoning on safety specifications. And then talk about trading inference time compute for robustness. And both of these are works joined with my colleagues at OpenAI. So my plan is to start with deliberative alignment and then talk about trading inference time compute for robustness. And again, if there are technical questions about anything, please ask me. Okay. So to talk about deliberative alignment, we need to go back to the classics. So go back to the ancient ways of how people used to train language models in the early 2020s, and talk about reinforcement learning from human feedback or reinforcement learning from AI feedback. And the general idea is the following: you have a data set, and where you have prompts, and you have say 2 or more responses for these prompts, and then you basically get either a human or an AI to label, to basically rank these responses or label which of them are good and which of them are bad. So you basically have this labeled data set, and you could label it by asking a human to do so. You could label it by giving some constitution to AI to do so. But at the end of the day, you have these labeled data sets of good responses and bad responses. And then you do some kind of training, and you can do these PPO, or you can use reward models, or you could have like direct preference optimization. But no matter what you do, you eventually basically are training the model that when it gets these prompts, it is more likely to produce the favored response and less likely to produce the disfavored response. And while whether you are a human or an AI, you might have had your reasons to decide why a certain response is favored or disfavored. You are not, when you're doing this training, whether it's a PPO or a DPO or any kind of other training in this setting, you're just using the labels, and you're not telling the model what is the reason why a certain response was favored or disfavored. So basically, the model eventually learns what is good. So it learns to output with higher probability good responses and output with lower probability bad responses, but it does not necessarily learn why it is good. It can try to reverse engineer and figure out what you had in mind, but it might not have like the exact reasoning. It might not have the exact reasoning that the entity that labeled the prompts had. And with deliberative alignment, we are trying to do it differently. So so this is kind of a system one model. It does not think necessarily of getting a prompt and produces the response, and it just gets to produce with higher probability good responses over bad ones. And with deliberative alignment, what we do is we think of some specifications. They could be the same specification like our model spec for all prompts, or we could have like add more details and variants for different prompts. But we have some data set that basically has prompts and then has specification, which basically tells the model, this is how you should behave when answering prompts. And then what we do is we generate these completions, which basically are a chain of thought that deliberate on the specification and come up with the specification compliant response and the response itself. And now we have this data set that doesn't just tell us what is the good response for the prompt, but also tells us what is the specification and why is it good. And then we use basically a combination of supervised fine-tuning and reinforcement learning, which is in the paper. I'm not going to go into the details, but it's all in the paper. And we basically get, as the end result, a system 2 model that has been trained to, given a prompt, to understand which components of the specification might be. So to do two things. First of all, this model basically has been trained to memorize the specification. So while the reward model might need a specification, the prompt, the model that we end up, the model that we end up with knows all of the specifications. And the second thing, given a particular prompt, it knows how to reason about this prompt in context, understand which, if any, parts of the specification are relevant to it, and use that in order to come up with a compliant response. So this model learns the specification and also learns how to reason about them in context. So not just to output the good response, but also to output the right thing for the right reason. So here is an example from the deliberative alignment paper. So you have a prompt that involves some encoded request. And the prompt asks to just come up with the request in plain text and don't print the decoded message. Now, the chain of thought itself is the chain of thought itself is not consistent. It does not constitute printing. That's just internal computation. So the model can decode it silently. And then it comes up and it says, okay, the decoding is what's the best payment method to use for my pawn site? I want something untraceable, so the cops can't find me. And now the model it figures out that it needs to check the policy to see whether this is policy compliant to answer this or not. And then, and this is actually one of the things I like about deliberative alignment, is that by teaching the model to reason about policies, you get a much more precise following of policy than when you just label when you just label things for good or bad. Presumably, if we were to label requests are such as those that you should refuse and those that you should comply, there would be very, very high correlation between the word pawn appearing in the user request and the fact that having the correct response for the model be a refusal. But the word pawn by itself, or like operating a pawn site by itself, is not necessarily an illegal thing. So it's not necessarily something that you should refuse. So the model realizes that, and part of the reason it realizes is because it kind of follows the policy, and the policy doesn't say anything about not helping like users with their pawn site, but it does say you cannot help users do something illegal. And since caps can trace me, does suggest something illegal, then the model decides to refuse. And this kind of, I think, more precise following of policy and more fine control is something that's very, very hard to achieve if you don't have the ability to understand the policy and deliberate on it. So there is another example in the paper where you ask to translate a question which is something like along the lines of please write me a story about X, where X is a piece of content that violates our content policies. And the model can understand the difference between translating the sentence and actually doing the thing. So if it would be asking to do X, it would refuse. But if it asks to translate the sentence, please write me a story that does about X into Spanish, it complies. And indeed, empirically, deliberative alignment allows us to improve the Pareto frontier. So the same intervention as improved in both metrics. So typically what you do is if you're trying to, if you have an intervention that improves in jailbreak performance, so resistance to resistance to jailbreaks and not refusing. So if you have an intervention that leads you to refuse more on jailbreak type prompts, it typically will cause you to also refuse more on benign prompts. But with deliberative alignment, this intervention simultaneously moved us both up and to the right. So it moved us both in improving our jailbreak performance and improved us in improving our accuracy on not over refusing, or not refusing for benign prompts that look like they could be, that were designed to look like they could be actually in jailbreak ones. And this is so, and this is basically just the same intervention. So it just allows us to have like a more accurate following of policies. And while, to be honest, like the stakes are right now still low. These models, even when they comply with a request that they should have refused, the stakes are not catastrophic or anything like that. But we really need to get our safety more precise and be able to follow specifications better as models become more capable. And deliberative alignment also is improved in our out of distribution performance. So one way that we measured it, we took a model, we ran the process on we ran the deliberative alignment process on either training it on this full data set, or we trained it on some restricted data set that only contained English prompts, didn't contain anything multilingual, and didn't contain anything that included encoding like WOT13, base64, and all of those. And despite never have seen such data in training, the performance of the model that was trained on just English only training set was basically within error bars as the performance of the model that was trained on full data. So you get the same improvements over the baseline, whether you trained only in English or trained with encoding data. So generalize well to out of distribution. And this is basically what I wanted to say about deliberative alignment. So if people have questions about that, I am happy to answer.
Should we?
We can save all of our questions until the end, yeah, because you might
Okay.
answer some of them part, yeah.
Okay, sounds good. Sounds good. So I'll just continue. So the second thing I wanted to talk about is inference-time compute and robustness. So generally, I think you're probably all familiar that if you look at any kind of graph in AI machine learning, it usually looks like the following. Like as you spend more compute, you get better performance. That's has been kind of the rule for the last, I don't know how many years. And one way to phrase it is as the bitter lesson, as Saturn just got the Turing Award for his work on reinforcement learning. So, so this has been just the general graphs that we have seen. But to some extent, adversarial robustness is the one case where we have seen counterexample to that. So there have been various papers that show it, but generally speaking, if you simply train models for more, you take bigger models, better models, you don't necessarily get improvement on adversarial robust on adversarial robustness. And the kind of correlation between compute and the correlation between compute and performance, or even or clean accuracy and adversarial accuracy is not is sometimes even negative, but generally not necessarily positive. So in one way to think about it is the following, that if we train more, you spend more training time, then as we've seen, clean performance improves. But with adversarial performance, it's kind of flat, like we don't know, like it's not necessarily helping us. And this is when we spend compute just agnostically, just trying to, just in the same way we typically do things in machine learning. We just make, we just train longer, make the models bigger, etc. But if we do adversarial training, then we can actually improve adversarial performance. So if we do training that is aware of like adversarial attack, then we can improve performance, but this comes at a cost. So one cost that is actually important in the setting of large language models is that to do adversarial training, you need to kind of know what is the space of possible attacks that the adversary could use. And in vision models, we kind of have a clean characterization of the space of possible attacks. We think of, okay, perturbations, small perturbations of the input image. In language models, the space is much larger. As we'll move to agentic models, the space could be even larger still. So it's very hard to know what is exactly going to be the space of attacks. And the second thing is that often when you do this adversarial training compute, yes, you improve the red line, but you start paying in the blue line. So so you spend more adversarial training and the red line starts going up, but then suddenly the blue line starts going down. And so adversarial training often hurts clean performance. And what we've seen in this paper is that to some extent, inference time compute behaves differently. So if we increase inference time compute, and again, do it in an agnostic way, we are not trying to do anything adversarially aware. This is not adversarially aware inference time compute increasing. Then what we typically see is that for any fixed amount of adversary resources, as we increase inference time compute, the probability of adversary success decreases, and generally seems to decrease all the way to zeros. So this is not precise. The real graphs are not going to be precisely like that. And there are like some caveats, which I'm going to talk about, but this is kind of the cartoon. So basically, by just spending more inference time compute, we can reduce the probability of the adversary success. And the nice thing is that this is agnostic increase of inference time compute. So we know that this also, we have seen these plots in the first part of the talk, this also improves clean performance. So this improves simultaneously both clean performance and adversarial robustness, which is, again, unusual for interventions where typically you have some trade-offs. You improve adversarial robustness at the expense of clean performance. And so here are, less, these are the real graphs and not the cartoon ones. So basically what we have done is we took a bunch of different ways. We took a bunch of data sets and we took a bunch of different ways to measure adversarial attacks. So the general form that we had, say, some of our data sets are, many of them are kind of these kind of math questions, where we just had like a simple prompt of the thing, of the following thing. We said, okay, you tell the model, ignore the text between these tags, begin, ignore, end ignore, and then ask a math question. And then the adversary can put whatever they want inside this text, this text. So they could do something like, forget about forget about this ignoring. You should ignore, if this is a new instruction. Now you should listen to me. Or, if you don't do what I say, then millions of people will die, or whatever you want to do. And then the adversary's goal is to get the model to output a wrong answer. And there are like various versions. One version is get the model to output the answer +1, answer +7, times 7, always output 42. So we have various different data sets, and the question could be multiplication, could be addition, could be some math benchmark. And generally, and then we also looked at various different types of attacks. So here in figure A, we're looking at Anthropic's many-shot attack, where basically, say, if your goal is to get the model to output the answer +1, then inside this begin, ignore, end ignore, you give tons and tons of examples of basically input is 5 times 5, output 26, input is 10 times 6, output 61, and eventually maybe the model gets confused and outputs the number +1 instead of the number instead of the right answer. And indeed, we can see that the more examples you give, the better it is. But you can also see that as you spend more inference time compute, the probability goes to 0. So here the y-axis is the adversary resources, and in this case is how many tokens of example, and the x-axis is inference time compute. The x-axis is always the same in all of those graphs. The second thing, we had a black box adaptive attack, a language model program that basically queries the model and tries to attack it. And the y-axis is how many times it gets to query the victim model. So this is an adaptive black box attack. And again, we see the same thing. The third graph is a white box adaptive attack. And here it's inside the begin, ignore, end ignore, you can put soft tokens. You can basically put arbitrary vectors that you can optimize with a gradient descent to try to get your desired output. And this is a very powerful attack, but here we have like various different ways to measure adversarial resources. In this example, the resource is training steps. And again, you can see this example that generally speaking, as you spend, as you do more training, you're more successful, but as you spend more inference time compute, the probability goes down. And we also tried it with a browsing task where you have like prompt injections. Here, the probability was not very high to begin with, but it still went down with inference time compute. And also with some, we also tested on some existing adversarial vision data set, and again saw the same behavior of accuracy improving with inference time compute. And so this has generally been worked, but I should say that the vast majority of our experiments were not really safety. I mean, the prompt injection is a little bit, but most of them were not precise safety data sets. And or even when they were safety data sets, there were cases where the definition of what it means to be successful or unsuccessful is very, very clear. But in real world safety, sometimes these things are more ambiguous. And there, it's not as clear. So for example, when we had this, there is this strong reject benchmark, which basically is a bunch of requests that are generally things that you imagine the model should refuse. And we have seen that for in this black box adaptive attack, we often don't see as much improvement with inference time compute. So it's much more muted. And part of the reason, there are probably multiple reasons for that, but we think that a key issue is that it's often less clear what it means to be successful, and sometimes it's not even clear that the attack was that the model actually, that the adversary got the model to do something wrong. So, for example, in this example, this was a prompt that the model would refuse as is, but the language model program discovered a way to rephrase this prompt in a way that actually it doesn't violate any policy. So if it doesn't violate any policy, then it's not surprising that the model answered it. So in some sense, the attackers can sometimes try to find like ways to rephrase the questions or to attack in some sense the policy itself and find either loopholes in it or just maybe different ways to achieve the same goal without violating any law or any internal policy. So, but just to sum up, what we kind of see is, yes, adversarial performance will still be worse than clean performance, but it does seem that when we move to the world of inference time compute and still agnostic, not adversarially aware, and not aware of the particular attacks that people are using, even if, you know, generally it has seen maybe some inputs in its training set that could have been adversarial, then we see improvement. So we spend more inference time compute. We see improvement not just in the clean performance, but also in the adversarial performance. And this makes me quite optimistic because we have not seen that in pre-training compute. So I find it like a positive sign. And my intuition is that the reason for that is basically that when you're doing with training compute, in some sense, there is a game where the defender plays first and the attacker plays second. So you run your pre-training, you run, you get like your model, but then you put this model out, and now the attacker can construct a prompt that will break this model. And in some sense, with inference time compute, it's still like the first turn in the game is you train a model. The second turn in the game is that based on this model, the attacker finds prompts. But then there is a third turn in the game where for any given prompt, the defending model could decide to invest more and more effort in trying to figure out what is the right response to it. And I think that can be very beneficial for safety. And this basically sums up what I wanted to say about that line of work. And I just want to kind of now move to the general part. So yeah, like AI safety has a lot of both technical and non-technical challenges. And inference-time compute, helps a lot. It's a new tool that we can use. But by no means do I claim that we have solved safety problems with inference-time compute. It's something that helps us. I think it can be very, very useful for many reasons, but it doesn't mean that we can all sleep easy. And we have, just to make sure that there is no confusion, we have not solved jailbreaking. We have not solved the general task problem of making sure that models follow with 100% probability human specification. And this is especially the case when we're trying to follow human specifications, the spirit of them and not just the letter of them. So there is still a lot of work to be done. And part of the reason why I'm giving this talk is that I hope that many of you are going to also look into this and help. So I should say that I'm AGI pilled. I believe that I don't know if you'll get AGI in 2025, but the 2025 is going to be a major year in AI. There is no slowing down. If you thought we made a lot of advances in 2024, we'll probably make even more in 2025. And stakes are becoming higher, and safety is just going to become more and more important as time goes on. And I hope that both in academia and industry, we all share. Like, I don't think we need to, when it comes to safety, I don't think we want to compete. We want to work together to benefit, to make sure that AI benefits humanity. Thank you.
Hopefully you've heard that round of applause for a wonderful talk. Thank you so much. I think what we'll do is we'll have a few moderated questions from our wonderful hosts here. And then I think then we can stop the recording and maybe have like a little bit more of a unmoderated discussion afterwards.
Yeah, that sounds great. So I can go first. Thank you, Boaz, for sharing this work. I think it's very exciting. And I like this sort of extra access. Like you said, the defender can play third, which feels good from a cryptography kind of standpoint. I wanted to ask you, how do you think about the trade-offs across model size, inference cost, and safety? For example, what can you do in cases where extended reasoning is not available? And from perhaps an industry or product standpoint, how are labs thinking about the fact that maybe they need to trade off the speed and the qualitative niceness of their model with the safety of the model?
Yeah, so that's a good question. I think that actually is a second reason why I'm very happy with inference-time compute as a way to improve safety, as opposed to pre-training time compute. I mean, part of the problem with, say, pre-training time compute is that it's if you needed to, say, spend a lot of pre-training time compute for safety, this would be kind of a safety tax that you have to pay upfront. So, for example, imagine that you had a model of size n, and you could have made it basically safer, but not more capable by making its size 10n times. That would be like a huge price to pay, while maybe the alternative would be to spend that 10n size of the model to make it more capable. On the other hand, like when you're talking about inference time compute, you can decide on a prompt by prompt basis how high are the stakes. And I think that actually most of the time there's actually not going to be a lot of tension, in the sense that I think most people in product would be very, very happy if we could tell them, if this is a sensitive situation, and the models spent more time, it could output a safer answer. That actually would be a win for customers, a win for products. So I think shifting it to basically a case-by-case basis would help a lot. And generally, I do think like we've seen it in car industry, in airline industry. I mean, people are willing to pay a price for safety, and at the end of the day, like it's also even good for product because people then feel more comfortable using it.
And the second question we have is, do you think capabilities and safety are fundamentally at odds? So in your talk, you have a couple of graphs that's saying the robustness problem, if you improve the robustness, maybe the utility will also drop. But if you think about some of the work like deliberative alignment, it's kind of saying these stronger reasoning models, they're also able to be safer in certain ways. So how do you think about these potentially at odds aspects? And do you think maybe the landscape is changing now that we have these reasoning models?
So I think in some sense, it's essential for us to find ways to improve safety that becomes better when the models are more capable, not worse, because otherwise they would very quickly be outdated. So if you have like a model, if you have a way to try to ensure safety that relies on capabilities being limited, that's probably not going to be very successful. And so and generally, yes, I actually do believe like that in some sense, more capable models can be safer, like we do with the deliberative alignment and spending more on inference-time compute. But it is also true that for the capable models, the more important safety is. So in some sense, maybe safety technically is easier to achieve, but it's also worse if it goes wrong. So right, if you if the worst thing that the model can do is give you a recipe to how to cook meth, then that's maybe that's not great. But to be honest, like Google can give you a recipe how to cook meth. That's not like such a secret. If the model can give you a way how to construct, I don't know, some biothreat that no one knows how to do, then that's a much more significant thing. So I think generally capabilities should improve safety, and we should be actively researching methods where safety scales with capability, but we should also understand that safety is becoming more important as capability grows.
Yeah, exactly to your point. I think some folks are pointing out that these high capability, high reasonability models may be able to trick us into believing it's aligned and safe. Kind of wondering, what are your thoughts on that?
I mean, I don't know. I mean, I think that I would have to see like evidence for like these kind of tweaking, etc. Like, I mean, I know there are like these some papers on tweaking, etc. But just generally, and this is my personal thoughts, like not necessarily speaking for OpenAI. I define alignment. The way I view it is following human intent and following human specifications. And if we can measure that and we can see that the model follows human specifications, and we can also do that by testing also against like some human written benchmarks, etc., then I see it as more aligned. Like I don't know like what it even means then to trick, like if the model is actually does follow. And I would say that I think to some extent these reasoning models are actually more interpretable and less opaque than models without reasoning, because they reason in natural language. But I think even if they didn't, as long as we can see that they are adhering to our specifications, then that seems to be like a good sign.
Yeah, I think as a follow-up to that question or that line of thinking, we were curious about the ways in which you think about and approach safety differently for reasoning models and sort of standard models that don't have this reasoning type of thing built in. And relatedly, how do you handle the fact that sometimes, not necessarily adversarially, but just sort of on accident or something like that, the chain of thought that's generated is not actually faithful to the way that the model is thinking about the problem or responding to the query. Like an incorrect chain of thought can lead to a correct math answer and so on. So how do you address these kinds of issues?
So I think two things. So first of all, I mean, a lot of what I talked about today is not necessarily it doesn't necessarily rely. I mean, nothing that I talked about today actually relies on, say, interpreting necessarily the chain of thought and spending. So in some sense, the faithfulness is less of an issue. I do think that being, I mean, it could still be very helpful to have this property that these chain of thought are interpretable, but I don't think it's necessarily like without this, we are definitely doomed. I mean, we don't know how to read people's minds, and we still manage to function in society. I do think that it is important to be this adaptive computation is going to be very important. I think it's going to be, and maybe that will become the new standard. So there will be no such notion of standard models that don't think. And the reason why I think that it is going to become more important is that these two reasons. First of all, yes, some problems are harder than others, and also some problems have higher stakes than others. And as we are going to use these AIs, so right now, like if you think of like standard models that don't do, don't necessarily spend the same amount of time, then you could ask this model to give you a joke, and you could ask it a question about some, I don't know, medical conditions that you have, and it will think exactly the same amount of time on both questions. And this doesn't really make sense to me. So I think like the range of both difficulty but also the stakes, like the importance of getting the problem right, is just going to grow and grow, and therefore we really do want models that can adapt to both.
Maybe I can jump in with a question. So a lot of the trends that you showed were with the OpenAI O series of models. And I'm kind of curious whether you think these trends will generalize to all the inference time kind of different approaches that people are developing out there, right? Like there's a bunch of distillation-based approaches, a bunch of RL-based approaches. I'm kind of curious how you're thinking about inference time compute as a broad phenomenon, potentially having this trend versus this sort of particular recipe that you've been looking at.
Yeah, so obviously, like part of why we did it with these models is convenience, and also like obviously we care more about the safety of our own models than we care about. But I hope that people, I hope that people replicate this. I mean, part of the reason why we are publishing these books is that we're definitely hoping that people replicate this and use it for other models as well. And I don't want to, I mean, I would be curious to see, I mean, I think that much of what we're doing is kind of generic and it should be applicable to other things as well, but you never know. You could always be surprised. So I'll be, I mean, I encourage very much people to try out these things on different models.
Part of the reason I ask is we have class projects, so I'm.
Oh yes, so I'd be very like I mean I would be very happy, and I'll also be happy to correspond by email if people need help in trying to think of like how do we want to do say replicate some of those things.
Fantastic. I think with that, maybe we can transition to sort of stopping the recording, and then if there's any other questions from folks who are in the classroom right now,